Welcome to this introduction to protection. I would like to start here with a few very basic questions. What is protection? Why do we need protection? Where is protection installed in a network? Let's start with the first one. Why do we need protection? Against what does protection protect? If we look into our systems, components may have faults. You see here a nice photo of a thunderstorm hitting a substation, and it may start a short circuit in a substation. Another event could be street works, for instance, hitting a medium voltage cable in the street and also generating a short circuit there. That means short circuits will happen. Protection cannot protect against short circuits, but protection has to do something if a short circuit comes. The main focus in this introduction will be short circuits, but you should be aware that we also have other types of problems like interruptions, overloads, overvoltage, undervoltage, and so on. So there are a lot of other things which can happen. So why or what do we have to do after such a short circuit? If we have a short circuit on a line or on a cable, this device has to be separated from the rest of the system. It has to be switched off, and the decision to do that is the main job of protection. That means components which have faults must be disconnected. If we don't do that, what may happen? This nice picture shows such a situation. That is a picture from a real case. What you see here used to be a brand new transformer. During the commissioning phase, the different teams had some misunderstanding. That means in this case, the transformer was energized while the protection system was still not in operation. And unfortunately, this transformer had a problem in the bushing. That means when the transformer was energized, there was a short circuit in the bushing, big current flowing, and what you see here is the result of that thing because the protection didn't work. So you see, not proper working protection can have severe impact. It can produce damage, and even more, it can produce injuries of people if they are standing around there, or it can also endanger the stability of the whole system. That is mainly valid for transmission systems, for weaker transmission systems. Let me say for countries which are not interconnected very much to other countries. If in such smaller transmission systems, a short circuit remains there for too long time, and long can mean, for instance, 200, 300 milliseconds, then you can generate an instability of the whole system, which may lead to a collapse. So you see, protection is an important thing in the networks. And to understand where it is installed, we have to look a little bit into the network. This picture shows, just in a symbolic way, a grid, a transmission grid, which connects somehow the power stations with the cities and industry and so on. And these lines you see there are in reality, of course, bigger things that are not single lines. We always use three-phase systems. That means one line in this so-called single line diagram is equivalent to 3 lines on this tower. On the tower on the left-hand side, for instance, you see 2 systems, 2 times the 3 phases. What you also see is a so-called earth wire on top of the tower. This earth wire does not transport any energy normally. The reason for the earth wire is it is a lightning protection for the line, and it often also carries optical fibers for communication nowadays. What you also see in this picture is that every one of these 3 conductors of the system consists of 4 individual wires. That is state of the art for extra high voltage. It reduces the electrical field strength around the conductor. That's why it's a normal case for extra high voltage line. On the right-hand side, you see a distribution overhead line, medium voltage. In this case, 1 system, that means 3 conductors. And there we use just single conductors for the individual phases because the field strength is much lower there. If we now look at the connection points of this grid, that means the points where all these lines come together, it looks like this. There, every line, at the end of every line, we have a circuit breaker. Here you see 2 pictures of circuit breakers for high voltage systems. You again see the 3 phases. On the left-hand side, you see it for an open air switchyard. On the right-hand side, you see an indoor gas-insulated switchgear. And if we now zoom out this point a little bit more, it looks like this. That means we have not one point where all the lines come together. We have a so-called bus bar. And all the outgoing feeders from this substation are connected to a bus bar. And at the beginning of every feeder, you have such a circuit breaker and a protection relay installed. Always remember, this is a single line diagram. That means in reality, you have 3 bus bars available there. These slides here with the circuit breakers are pictures for transmission, for a transmission voltage level. The next slide shows the same story for a distribution level for medium voltage. In this case, it's an indoor substation. You see here the bus bar goes through this whole installation from left to right. And in every compartment, you see it's a big substation. We have many compartments there. In every compartment, you have 1 circuit breaker. The outgoing feeder goes down to the bottom. That means the cables are underneath. And you also see the protection relay installed there. If we now look a bit more in detail into such a feeder, it looks like this. You see on the left-hand side again the bus bar, and then I illustrated 1 feeder a bit more in detail. You see here the circuit breaker. That means that is the device which is really able to interrupt the short circuit current in case the line has a short circuit. Then we see current transformers and voltage transformers here. Why do we need that? The protection relay has to measure currents and voltages on the line to decide is there a short circuit or not. But as the line may have 20 kV, 132 kV, 400 kV or whatever, we cannot connect the line directly to the protection relay. We connect it via the so-called instrument transformers. That means the voltage is transformed down to a reasonable level, and also the big current which may flow, we may have 10, 20 kiloamps flowing in case of a short circuit. Also that is transformed down to a level which the protection relay can use. We typically also use a battery in a substation. It sounds a bit strange to have a battery in a substation which is full of power, but that battery is used to give a reliable supply, both for the circuit breaker, for the whole control system, and also for the protection relay. And what is also indicated here is the wiring. Of course, wiring looks a little bit trivial in this sketch. Yes, it's trivial, but if you think about a big substation, open air substation, then you have the circuit breaker, the VTs and CTs outside in the field. You always have to multiply what you see here by 3, because we have the 3 phases. And the protection relays are somewhere in a relay house. And now you can imagine you have a lot of wires, and these wires can be 100 meters long or longer. So sometimes also things happen with the wiring, so that we sometimes also have to pay attention to that. We can compare this arrangement a little bit with what you know from your home. This is an MCB you have at home, and this one does protection for your low voltage system at home. And it's worth looking at the differences. What does this one do? What does our protection relay do in a substation? Their job is pretty much similar, but on the other hand, there are differences. This device here directly measures the current. In this case, it has only current. That means the current flows directly through this device. It makes the decision. If it says, okay, there is a short circuit, I will trip. It also interrupts the current. What our protection does is only half of that. It cannot measure the current directly. It gets the current and voltage measurement through current and voltage transformers. But the important thing, it cannot interrupt the current itself. It can only give a trip command to a circuit breaker. That means our protection relay roughly does half the job of such an MCB, but of course in a much more sophisticated way. What you also sometimes find is this arrangement, which is unfortunately a little bit more complicated. That is a so-called breaker and a half substation. It sounds a bit strange. Where do we have half a circuit breaker somewhere? What is the structure there? On both sides you see a bus bar, and to the top we have 2 outgoing feeders. And in this arrangement, we again have 1 protection relay per feeder. The left protection relay for the left-hand feeder, the right protection relay for the right-hand feeders. But we have in total 1, 2, 3 circuit breakers. That means for 2 feeders, we have 3 circuit breakers. That ends up in an average 1.5 circuit breaker per feeder. That means if we look at the left-hand relay, this is responsible for the left-hand feeder. If this relay detects a short circuit on the left feeder, it has to trip 2 circuit breakers, the left-hand circuit breaker and the center circuit breaker. The same applies to the right one. If that detects a short circuit on the right-hand feeder, it has to trip the center circuit breaker and the right circuit breaker. You also see voltage transformers and current transformers here. In this case, the situation with the voltage transformers is pretty easy. So we have a voltage transformer on the feeder. That means the left-hand relay measures the voltage on the left feeder. The same applies to the right one. The current measurement is a bit more tricky in this case. As you see here, the current transformer is not in the feeder. The current transformer is here, or several current transformers are here in this so-called diameter. Diameter is this horizontal connection between the 2 bus bars. And in order to measure the current in the feeder, for instance in the left-hand feeder, the protection relay has to sum up 2 current measurements in the diameter, and just by summing up the currents, it can measure the current in the feeder. But the rest behind that, the protection principle, the way to identify short circuits is the same as in the previous drawing. This is called breaker and a half substation. And the decision whether we build single line or double busbar substations or such a substation, that comes from the primary system, from the high voltage system. The protection people have to adapt to that. Let's also have a short look at the instrument transformers, just to show a few examples. On the left-hand side, you see a voltage transformer and a current transformer for medium voltage. You see here the connection points for the voltage and also for the current. That means the current flows through the current transformer this way. The primary current in the line is connected to this one. And our protection relay is then connected here in the bottom at these terminals where we see the transformed voltage and also the transformed current. On the right-hand side, we see the same story for the higher voltage levels, in this case 400 kilovolt. In this case, you don't need more power in the current transformer and the voltage transformer. These things are just bigger because we need more insulation. Because we have to measure a voltage on a 400 kV level and need insulation for 400 kV. You see here a current transformer for 400 kV. The current flow is here through the top of this thing. We also see a voltage transformer where the voltage is connected and our protection relay is connected somewhere down there. Just on the right-hand side, you see a combined instrument transformer. It is a combination of a current transformer and a voltage transformer in one device. Because normally we need both measurements, current and voltage. And what you also see here is again the three phases. That means if we talk about one voltage transformer, we normally talk about 3 devices, 1 per phase. Now let's talk a little bit about the requirements to protection. And there we often mention the 3 S. That means speed, safety, and selectivity. So let's look at this a little bit more. What does speed mean? Imagine speed is pretty important. Remember, short circuit, lot of current flowing, risk of damage and of components. That means we must be fast to disconnect the fault if we detect one. And in protection, fast means something like a few milliseconds up to 100 milliseconds, or in cases even more when we have to do compromises. Getting enough speed is, on one hand, a question of the algorithms. That means on the manufacturer side, developers have to invest brain into fast algorithms, especially for the high voltage, extra high voltage levels. But speed is also influenced by the protection concepts. And you will see in the second part of this webinar that we sometimes have to do compromises when building up the protection concepts, which will lead to delayed tripping. That means we have to reduce speed for some reasons. The second point is safety. Think it's self-understanding. It's technology. If our technology doesn't work properly, there is a risk of damage or injuring people or instability. That means we have to think about the reliability of the whole system. And there will be a separate chapter on that. And the last issue, which also has to be mentioned, is the selectivity. What does selectivity mean? Selectivity means if you have a short circuit somewhere in the network, there is short circuit coming through different lines, cables, and transformers. That means several devices in the system will see there is something wrong, but only the protection device of the faulty line or cable has to trip. The other ones see the fault, but they should not trip, because we don't want to trip 5 lines if there's a short circuit on one line. And this thing is called selectivity, that only the faulty component is disconnected from the rest. And that is a very important issue, and we will have several chapters dealing what can we do to get selectivity. That is the end of this basic chapter of this introduction. And in the next chapter, we will see what aspects do we have to consider if we want to put together a protection scheme. Thank you.